Okay, so we did a number of examples of limits in class already, and in this video I want to do a few more. Be sure to add these examples to your regular course notes. Alright, well, this first example that we have here, it involves trigonometric functions. And the general tip for working with trig functions when trying to compute a limit, or very often in general, is that if you can't quite tell what's going on with your function at first, try rewriting it in terms of sine x, cosine of x, or maybe by using a trigonometric identity. Alright, so in this case, we have the limit as x tends to pi by 2 of the function cosine of x over tan of x. And maybe you're not really sure about what's going to happen with that tan x at pi by 2. In fact, it's going to look like 1 over 0, so that doesn't seem like something that's actually defined. So in fact, this function isn't defined at pi by 2, but maybe you're not able to see that right away. So what we'll do is we'll rewrite tan x in terms of sine x and cos x, which is to say we'll write tan x as sine x over cosine of x. Alright, so this is equal to the limit as x tends to pi by 2 of cosine of x, and this divided by tan x, which we can rewrite as sine x over the cosine of x. Alright, and now we can rewrite this as the limit as x tends to pi by 2, so we're rewriting this to clean it up as, well, we have cos x, which we can write as cosine of x divided by 1, and this is all divided by the sine of x over cosine of x. So remember, when we divide by a fraction, we just multiply by the reciprocal. So we rewrite this then as cosine of x over the sine of x, and we can clean this up by writing this as the limit as x approaches pi by 2 of cosine times cosine of x is cosine squared of x, and this divided by sine of x. Now, looking at this, we can probably see fairly quickly that in fact pi by 2 is in the domain of this function cos squared of x divided by the sine of x. So in case you've forgotten, let's just draw here a little unit circle. So here's a unit circle for us, slightly ugly unit circle, but nonetheless, if we go to angle pi by 2, we see that the y-coordinate on the unit circle at angle pi by 2 is just 1, which is to say that sine x at pi by 2 is just equal to 1. So at pi by 2, sine x is 1, and so at pi by 2, we're not actually dividing by 0, and that means that pi by 2 is actually going to be in the domain of this function. So now we can rewrite this as equal to evaluating now, as I said, at pi by 2, because pi by 2 is in the domain of the function. Maybe I should do this. as I was doing in class, pi by 2 is in the domain. And, as we said, because pi by 2 is in the domain of our function, to evaluate the limit, all we have to do is evaluate at pi by 2. Okay, so this is equal to, evaluating at pi by 2, the denominator we said is going to be 1. And what do we get when we evaluate the numerator, cosine of x squared at pi by 2? Well, what is cosine of pi by 2? Cosine of pi by 2 is just the x-coordinate of that point on the unit circle at angle pi by 2, and the x-coordinate here is just 0. So we have a 0 squared. So 0, if you like, squared, and that is just equal to 0. Okay, so that completes that problem. Okay, let's try another one. All right, so this would be example B, and the limit here is the limit as x tends to pi by 6 of 1/4 minus sine of x all squared, and this divided by 1/2 minus the sine of x. Alright, so for this, let's once again take a look at our unit circle. The first thing that we should be doing, of course, is we should ask, is pi by 6 in the domain of this function? And it will be in the domain of this function, provided that when we evaluate at pi by 6, this denominator isn't 0. But in fact, you may recall that at pi by 6, so maybe I'll draw a new one here, slightly larger than the last one. So here's a new unit circle for you. Somewhat larger. Alright, if we go to angle, pi by 6 looks a little bit like this. Here's angle pi by 6. The question is, what is sine pi by 6? And sine of pi by 6, you might remember, is 1/2. Cosine of pi by 6 is root 3 over 2. So that is the y-coordinate at angle pi by 6. Sine of pi by 6 is 1/2, and the x-coordinate at angle pi by 6 on the unit circle, just to say the cosine of pi by 6 is just root 3 over 2. Alright, so with our unit circle. Okay, so what did we just say? We just said that the sine of pi by 6 is just 1/2. So at pi by 6, our denominator looks like 1/2 minus 1/2, which is 0. Pi by 6 is not in the domain of this function. So what do we have to do? Well, somehow we need to simplify this. Well, what you might notice is that in the numerator here, we actually have a difference of squares. 1/4 is 1/2 squared. And here we have minus, of course, the sine of x all squared. So what we have here is a difference of squares. So it looks like an a minus b, if you like, a squared minus b squared, if you like, and that we can factor as a minus b times a plus b. Doing that in this situation here, we get that this is equal to the limit as x tends to pi by 6 of, alright, our a a minus b here is going to be 1/2 minus sine x. So we write that 1/2 minus the sine of x times our a plus b here is 1/2 plus the sine of x, and all of this we have divided by 1/2 minus the sine of x. Okay, well, this is good because our denominator was 0 at pi by 6, and now we'll be able to cancel this denominator with 1/2 minus sine x, which we see in the numerator here. Remember, when we take the limit as x tends to pi by 6, we only care about values of our function for x close to pi by 6, but not at pi by 6. So for all x's that we're concerned with, x actually isn't equal to pi by 6, and therefore 1/2 minus sine x, this denominator, won't equal 0 for all the x's that we're concerned with. And so we have a non-zero number here for all x's we're concerned with, the same non-zero number up here in the numerator, and we can cancel. Okay, so this becomes equal to the limit now after we cancel as x tends to pi by 6 of 1/2 plus the sine of x. This is now equal to, we're good because we can now evaluate what we see here, certainly at pi by 6, and this is equal to 1/2 plus the sine of pi by 6, which, as we said above, is just 1/2, and so our overall answer is 1. Okay, so that completes that example. Okay, so our next example is this one. C. This one won't be a limit which involves a trig function. It's the limit as t tends to 0 of 1 over t times the square root of 1 plus t minus 1 over t. All right. Okay, so taking a look at this, we notice that 0 isn't in the domain of this function. Here we'd be dividing by 0 when t is 0, and here again we'd be dividing by 0 when t is 0. So it's definitely not in the domain of the function. And in fact, what this looks like when t is equal to 0 is something like this. It looks like a t is 0 on the left. There we have a 1 over 0, and then we subtract from that something that looks like 1 over 0. And what that could be, well, in fact, that could end up equaling anything. And at the moment, we really have no idea how to deal with something like this. So, somehow, we should try to simplify our expression here. And if you're trying to simplify a sum or a difference of fractions, usually what you should do is find a common denominator. So let's do that. So this is equal to the limit as t tends to 0 of, alright, so for our common denominator, well, we see t in both terms, so we can use that, and times root 1 plus t. Okay, so now, in this term here, well, we didn't actually change anything, so again, we can just put a 1 here, and then minus. And then looking at this term here, well, we multiplied the denominator by root 1 plus t, so we have to multiply the numerator by the same. And we have minus root 1 plus t here. All right, So now, looking at this, well, we see that this now is of the type, when t is equal to 0, well, our denominator is still 0, and in the numerator, when t is 0, we'll get 1 minus, so we'll get 1 minus the root of 1 plus 0, 1 minus 1, which is again 0. Alright, so this is now of type 0 over 0, and this is the sort that we've been dealing with for a while now. And looking at this, what's the problem? Well, the problem is that we have this 0 in the denominator, and that's being caused by this t here. So somehow, if we're going to be able to solve this, we're going to have to be able to cancel this t in the denominator with something in the numerator. But at the moment, there definitely is no t standing on its own in that numerator there. So somehow we have to get one there. And we'll use the same trick that we used with another example that we already did in class. We will rationalize the numerator. Alright, so we'll just rewrite this. This is going to be the limit as t tends to 0 of, alright, so just rewrite what we already have. 1 minus root 1 plus t divided by t root 1 plus t, and to rationalize, we are going to multiply numerator and denominator by the conjugate of what we see in the numerator here. So 1, and now plus root 1 plus t divided by 1 plus root 1 plus t. So we haven't changed our function at all because we multiplied and divided by the same number. We just multiplied our function by 1. Alright, so now we'll square this out, multiply this out, and we'll have the limit as t tends to 0. And what do we have? Well, this looks like an a minus b. This looks like an a plus b. When we square it out, we'll have a squared, 1 squared, minus this root squared. And when we square the root will disappear. Alright, so in the numerator, as I said, our a squared, 1 times 1 is 1 squared, which is 1, minus root of 1 plus t squared, which is just 1 plus t. And in our denominator, we have t root 1 plus t, and multiplying across, and really, don't forget these brackets here, times 1 plus root of 1 plus t. So be really careful with your brackets, as I have been in 2 places here. I was careful with my bracket here, and I was careful with my bracket here. If we're not careful, we can very easily make a mistake. Alright, so now this is looking really good because we have a 1 minus 1 in the numerator, and those are going to cancel, and we're going to be just left with minus t. So let's write that out. This is equal to the limit as t tends to 0 minus t over t root 1 plus t, all times 1 plus root 1 plus t. And now this is great, because remember, our problem with this limit was that in the denominator at 0, we had 0, and the reason for that was because we had this t here. When t is 0, that denominator is 0, because of that t that's sitting here alone. And so what we were trying to do right from the beginning was get rid of this t. We needed to cancel this t with something in the numerator, and by performing that rationalization trick, we see that we have a t in the denominator and a t in the numerator. We get to cancel them. Alright, so now we do our cancellation. This is the limit as t tends to 0. T over t is 1, so we'll have minus 1 in the numerator, then root 1 plus t, and 1 plus root 1 plus t. And now this looks really good because, well, if you evaluate this denominator here at 0, you will no longer get a 0 denominator. So in fact, 0 is in the domain of this function. Remember when we did this cancellation as well, I've said it quite a few times, when we are taking this limit as t tends to 0 up here, we only care what our function looks like for t close to 0, but not when t is 0. So for all t's we're concerned with, in particular, t isn't 0, and therefore we can do this cancellation. T over t is 1 when t is not 0. Okay, so now we return to this. The denominator is no longer 0, and so we can just evaluate at 0. Alright, so now we take the limit. I stop writing limit at this point because I'm actually taking the limit, and I get root 1 plus 0. Write it all out in one step here. 1 plus root 1 plus 0. And what is that? Well, it's minus 1 over root 1 is just 1, and over on the right we have 1 plus 2. 1 times 2 is 2. So our answer is minus 1/2. Okay. And finally, let's do one last example. So what will it be? Here we are. So what are we at now? D, I think. It's going to be this one, the limit x tends to 0 of e to the 3x minus 1 in the numerator over e to the 2x minus e to the x in the denominator. Alright, so as usual, we check to see what happens when x is 0. When x is 0, the denominator is going to be just 0. E to the 0 is 1 minus e to the 0 is 1, so 1 minus 1 is 0, and in the numerator we'll have e to the 0, 1 minus 1, so it looks like 0 over 0. Okay, so this looks like type 0 over 0. Maybe we have some hope with it, but it's not necessarily clear what we can do at the moment. So we should probably try to simplify this function somehow. And the first thing that probably comes to mind is that we can factor that denominator. This looks like e to the 2x minus e to the x. That's actually e to the x all squared minus e to the x. So e to the x is common to both of these terms. And if I factor it out, I'll have e to the x times e to the x minus 1. If you go backwards, you check, multiply through, you'll get e to the x squared, which is e to the 2x, minus e to the x. So that's correct. And now we have to look at this numerator here. Well, if I study what I have here, we see that the problem with this function is that when x is 0, this e to the x minus 1 is 1 minus 1, which is 0. So somehow I'm going to have to cancel this term if I'm going to be able to solve this limit. So somehow it would be nice if I could actually see an e to the x minus 1 in this numerator up here. And in fact, if you look at that numerator, what does it look like? It actually looks like e to the x all cubed minus 1. So in fact, this looks like, maybe I should rewrite it, write an extra line to make it clear what I'm thinking. E to the 3x, it looks like e to the x all cubed minus 1. All right, and 1 is also a cube. It's, of course, 1 cubed. So what we see in the numerator here is a difference of cubes. And you'll recall that a cubed minus b cubed can always be factored as, this is one that we want to know, a minus b times a squared plus ab plus b squared. Alright, so that's the factorization of a cubed minus b cubed. If you don't see that, by the way, you can always multiply this out and check that you get what you have on the left. Alright, so here we have an a cubed, and here we have a b cubed. We can write this then as a minus b times a squared plus ab plus b squared, where a is e to the x and b is 1. Okay, so let's do that. So now this is equal to the limit as x tends to 0 of e to the x minus 1, there's our a minus b, times e to the x all squared, which I can write as e to the 2x, plus e to the x times 1, which is to say e to the x, plus 1 squared, which is 1, and this all over, same denominator as before, e to the x times e to the x minus 1. Maybe I'll rewrite that as e to the x minus 1 times e to the x in the opposite order. And this is good because, as we said before, when x is 0, it's this e to the x minus 1 in the denominator, which is 0. So that was what was giving us trouble. We wanted to see this in the numerator. We now have it. For all x's we're considering, x is near 0 but not 0. So e to the x is close to 1 but not 1. E to the x minus 1 in particular is not 0. And there it is, again, in the numerator, not 0. This number over this number is 1. In other words, we can cancel. All right, so this is equal to the limit as x tends to 0. Do our cancellation, and we'll just be left with e to the 2x plus e to the x plus 1. This divided by e to the x. And now, looking at this one, you note that the denominator at x equal to 0 is no longer 0. E to the 0 is 1. So 0 is actually in the domain of this new function, whose limit at 0 is the same as the limit of our original function. And so we can just evaluate this at 0 to finish. Alright, so this is now equal to, then evaluating at 0 in the denominator, we just get 1, e to the 0, the numerator is 1, plus e to the 0 is 1, plus 1, our answer is 3 over 1, which is 3. Alright, so that's it.